Hello, welcome everyone to the afternoon session. And we will start with Abhinav Prem, who will tell us about topological order in open quantum system. Please.
Okay, yeah, so first, of course, let me thank Sergej and Subhro for organizing this beautiful conference. It's been, great being here and chatting with everybody. Oh, is it audible in the back? Okay, great, awesome. So I thought, keeping with the theme of generalized symmetries, I'll tell you about how generalized symmetries show up in the context of open quantum systems. So they're a different kind of generalization and how they let us define phases of matter, but now in this different context, going away from ground states of gapped local Hamiltonians, where we usually define phases of matter, but now thinking about open quantum systems. Okay, so we're interested in quantum many-body states with non-trivial entanglement, both from a fundamental perspective, but also because quantum many-body states with non-trivial entanglement, they give us resources for tasks in quantum information storage and processing. So we know, for instance, if you have SPT states, they allow quantum teleportation, and you can do measurement-based quantum computation with them. And of course, topological order is famous for permitting, it can store a quantum memory, and we can do quantum error correction. And one of the main properties of topological phases or gapped phases exactly, is that these properties, the fact that you have some state and it's a resource for a task in quantum information, is not just a property of a particular state, but it's actually shared by all states within the same phase, right? And this is why they're interesting. If they were just properties of a particular state, then okay, you have to work very hard to prepare a certain state, and then if there's any perturbations, you go away from that, you lose your kind of resource that state provides. So they're interesting because they're properties shared through the whole quantum phase. And as we heard in Michael's talk, recently, these interesting states have now been realized on these quantum devices. So the toric code, for example, even the non-abelian D4 topological order has been realized on quantum processors. But these devices are not just sitting in isolation. So even though experimentalists have made tremendous progress in isolating these systems from the effects of thermal noise up to fairly large timescales, there's still other incoherent processes in these systems that we can't ignore. And so if we want to understand what are the resource theoretic properties of these states under noise, we need a notion of mixed state phases, right? When we take a state, our favorite state, the toric code, and there's some amount of noise acting on it, is it still a good resource for storing quantum memory, et cetera? So we need a notion of mixed state phases of matter, which is kind of the rough motivation for this work. Okay. So phases of matter, we mostly understand them just for pure states evolving under unitary dynamics. There's some local Hamiltonian, or there's some unitary acting on your state. So we can even think about Cloquet topological phases, for instance, but this is still unitary dynamics. But open systems are ubiquitous. So a very trivial example is just if I take a magnetic impurity and I stick it into superfluid helium, I can think of the impurity as being my system of interest. I can trace over the rest of the droplet, and then I get an effective open quantum description of my system. So what happens? I take some pure state, and I let it get entangled with the environment. And generically, what happens is that the system loses its coherence. Right? There's some phase coherence over here. The pure state evolves into a mixed state. Here, by a mixed state, I just mean a stochastic mixture of pure states, and all the interesting entanglement is just gone. So this is typically what happens when we let a pure state interact with an environment. And sort of one thing we've known for a while is that thermal states are typically featureless, especially below 4 spatial dimensions, although I should advertise Tibor's talk next week, where he'll discuss an interesting thermal state in 3 spatial dimensions. But for instance, it's known that the toric code is not a good quantum memory below 4 spatial dimensions, so it's not thermally robust. And so from a topological perspective, thermal states are kind of boring below 4 spatial dimensions. But thankfully, the only option we have is not just coupling to a thermal bath, and there are many other kinds of open systems or open dynamics that one can think about. And the reason this question has become interesting now, in particular, is because we're living in the era of controllably open quantum systems, where we're not just limited to coupling the system to some thermal bath, but we can design the kind of noise approved. So if I want topological order, right, for instance, below 4 spatial dimensions, or more specifically, if I want a quantum memory or a self-correcting memory, we know that's not possible below 4 spatial dimensions. So the 4D toric code, for instance, the 4-dimensional toric code, right? The string-only toric code, right? That's thermally stable. So that's the simplest example. If you want something in 3 dimensions, you could have sort of a one-form SPT, but that's very fine-tuned. So if the one that Tibor will discuss, so it is a non-trivial kind of mixed-state topological order, but it still does not preserve quantum memory. So from a resource perspective, it's still trivial. Yeah.
A naive question. Suppose one can prepare a mixed state that has some sort of topological order. Can it be used for the purpose of quantum computing? Because most of the discussions of quantum computing are done in the framework of pure states.
Indeed.
You apply unitaries and so on. But is there a generalization of quantum computing with mixed states?
So indeed, as I'll discuss, the notion of a mixed state phase is related to the resource theory of mixed state phases, of these mixed states. So we consider a mixed state to be non-trivial if it can still store a non-trivial memory, for instance. Yeah, so I'll get to that. Yeah, thanks.
That there are some criteria for mixed state to satisfy so that it can
indeed
be a resource for
exactly
quantum information processing.
Exactly. Yeah.
Okay.
Yeah. And that's related to the notion of mixed state phases, intimately related. Yeah, please interrupt with questions. The organizers were generous and gave me 15 extra minutes exactly so I could, we can have more discussion. Okay, so right, so this is just to, motivate this, why this question has become particularly interesting now, because we have all these kinds of different devices. So, you can take a 3-dimensional topological insulator and put a 2-dimensional magnet on its surface, and the effective dynamics of the system, it turns out it realizes, is just a Schrodinger equation, but with a Hamiltonian that turns out to be non-Hermitian, right? So this is kind of one generalization to going beyond just unitary dynamics. Kind of more concretely, one can think of some circuit or cavity QED setup where you can drive the system with a coherent laser, and then there's some photon loss in your cavity. And then the effective dynamics in this case is just governed by some Lindblad type master equation, where all the coherent dynamics is just given in this usual von Neumann part of the equation. And then you can encode all the jump processes in these effective jump operators, and I'll get back to this. And then in these quantum devices, of course, what's really happening is you're trying to prepare with, maximum fidelity, some state that you're interested in, let's say in trapped ions. But then there's some noise acting on the system, and this noise only acts to some finite time, and I can model this through just a quantum channel, so a finite depth quantum channel given here in the Krauss representation. But one nice thing is that decoherence is a non-unitary process. So it's a new knob that we can use, and we can ask, are there new kinds of phases that we can obtain once we use kind of the power of non-unitary processes, right? So is it possible to use non-unitarity instead of just trying to protect our states from decoherence? Can we use non-unitarity as a knob and then get new kinds of many-body phases, which could potentially give us new resources for tasks in quantum information processing? And so this sort of opens the possibility of intrinsically mixed state order. And for the purposes of this talk, what I'm going to mean by intrinsically mixed state order are patterns of many-body entanglement that we believe to be forbidden in the ground states of local Hamiltonians. Right? So I'll take that as my definition of intrinsically mixed state order. So as Julien very nicely discussed, we believe that ground states of local gap Hamiltonians in 2+1 dimensions are fully classified. And the data that classifies these is that of a unitary modular tensor category, right? So these were introduced over the last 2 days, so we should all be familiar with these. And then an alternative perspective that Hotat introduced today in his talk is that we can think of these topologically orders as being given by the spontaneous breaking of some generalized one-form symmetry. We have these 2 different perspectives on topological orders in 2+1 dimensions. And I'll mostly focus on 2+1 for today. So you also need a mixed anomaly, indeed. Yeah, I agree, yes. It's not sufficient to just say spontaneously broken one form. But the key assumption behind this classification is that we have unitary quantum dynamics, right? So ground states of gapped local Hamiltonians, or as I'll briefly discuss, equivalence of states under finite depth local unitaries, right? But now we want to generalize beyond this and allow for some kind of noisy dynamics. Okay. So exactly, that's the question I want to ask. Can we get new topological phases that are intrinsic to open quantum systems? And then can we make some attempts to classify them in the same way that we've classified ground states of gapped local Hamiltonians? Okay. And then a related question that I'll try to get to towards the end of my talk if there's time is, can we get steady state topological phases? So here I'm just asking, suppose I have some state and noise acts on it for a finite time. What is the classification of these density matrices? Here I'm asking a slightly different question. I'm saying I have some state, and then can I get a non-trivial state as the steady state of my long-time dynamics, right? And these two are separate questions. And so really there's some noise rate, and as a function of this noise rate, is there a region in my phase diagram where I'm in some mixed state phase in the steady state, and then after that the noise is too high, and then we end up in the trivial phase. So what's the notion of stable mixed state phases, and can we stabilize topologically non-trivial steady state phases using fully local dynamics? So that I'll get to towards the end of the talk. Okay, just to flash the main results. So what I'll do is I'll study so-called error-corrupted topological orders in 2 spatial dimensions, and I'll classify these using the language of strong non-modular symmetries. So the notion of modular tensor categories was introduced again in Julian's lectures. So here I'll show that in mixed state phases, you can actually realize non-modular anion theories. That's the generalization. The way I'll proceed is I'll just take something we understand, so just a pure state topological order, or on the lattice, just some nice stabilizer code, and I'll add some local noise to it. And I'll ask what happens to the symmetries of this state when I add maximal noise, where I can study this analytically. And it'll turn out that the stabilizer code turns into what's called a subsystem code, and then our modular symmetries turn into non-modular symmetries. And I'll explain all of this. And then one thing we use this for is to identify real platforms which have a non-trivial mixed state topology. And then we were able to find the first practical proposal for local topological memory in 2 spatial dimensions, which has been sort of an outstanding question in the field. Yeah. So because I'm starting with some pure state and just adding noise to it, right? You could imagine obtaining mixed states in some other way. So I don't know a counterexample to this, but I also don't want to claim a full classification. So it's only in this restricted setting of, you could perhaps lift some other conditions that I'm not aware of, or at least this is a very physical way of getting these mixed states. But you could ask, what are the possible phases of just mixed states in general, not obtained through decohering pure states? And I believe the 2 are equivalent, but I don't know. I don't want to claim a proof. Yeah. I'm not aware of any counterexample. There's a nice math paper by Ogata earlier in 2025, and she confirms this using an operator algebra perspective. But again, that's not my work, so I don't want to claim that. Good. So any mixed state that you could realize as the ground state of a gapped local Hamiltonian, that I'll just call as mixed state topological order. Intrinsic mixed state or mixed state topological order, or any intrinsic mixed state phase specifically, is what you cannot get in the ground state of a gapped local Hamiltonian in the same spatial dimension. So in D equals 2, for example. Yeah. In this case, the main difference is modularity. Yeah, you just lose modularity. So that's what it means. It means braiding degeneracy. So your braiding becomes degenerate. That means there's some anion in your theory that you cannot detect via braiding with other anions in your theory. Yeah, I'll define it again.
Just to re-ask Ashwin's question, so this pure state topological order and this intrinsic mixed state topological order would be completely decoupled in the sense that this mixed state topological order that you would get has no connection to...
No, that's not true. It's descended from the pure state topological order.
Okay.
Yeah, it inherits its structure from the pure state topological order, and that's how we're able to classify it.
Okay.
Yeah. Good. So in 1D, we could think about SPTs instead of mixed state TOs, and then these so-called intrinsically average SPTs would be the ones that correspond to what I would call kind of intrinsically mixed state phases. And those are kind of, those descend from taking a gapless SPT and decohering it. So again, that's something that you can't get from a gapped Hamiltonian. I see what you're saying, in 2 plus 1D. So you're asking about 2D SPTs. So here I'm just thinking about, I'm not imposing any symmetries. I'm just purely thinking about topological orders. Yeah, we can discuss SPTs offline, but there's a way to think about those. I will, as one form, as generalized one form symmetries. Yeah. Not a zero form. Exactly. So the subsystem codes descend from the stabilizer codes, and I'll show how that happens. Yeah. Exactly. Yeah. No, that doesn't fit in here. There's specific subsystem codes. I'll discuss them. Okay. So, okay, just papers, and these are 3 papers, and these are wonderful collaborators I work with. Okay. So outline, I'll first go over intrinsically mixed state topological order. And then if there's time, I'll discuss how we get steady state order using so-called erasure cables. Okay. So this, I guess we haven't specifically seen this week, but so what is the equivalence relation for pure states? If I want to classify states, right, I have the space of all pure states in 2 dimensions, and I want to put some equivalence relation on them. Equivalently, I have the space of all Hamiltonians, gap local Hamiltonians, and I want to put some equivalence relation on them. So the usual one that we put, we say 2 Hamiltonians are in the same phase if I can find a smooth deformation between H1 and H2, specifically such that the gap remains open in the thermodynamic limit, right? So if I can go from H1 to H2 in such a way the gap never closes, I say that H1 and H2 are in the same phase. I can also define an equivalence relation just at the level of states. So we can say that 2 states, psi1 and psi2, are in the same phase if there exists a unitary, right? But a finite depth local unitary that transforms U1, psi1, psi2, right? So if you want to be very careful, you can be quasi-local and the depth scales logarithmically with L, but those are details we don't have to worry about. So if I can find such a unitary that takes me to psi1 to psi2, we say that these are in the same phase. And again, I'm not imposing any symmetries here. Yeah. Well, if you want to get, yeah, most cases I know if you don't need the polylog. It's just a technical detail, yeah, in Hastings proof. Yeah. That's right. Yeah. So suppose I just consider the, all short range correlated ground states of gap bosonic Hamiltonians in 2 plus 1 spatial dimensions. What does this definition do? It just partitions this space into different topological orders, right? We're not imposing any symmetries. You just have the trivial topological order, so all invertible states, SPTs would be sitting in here. And then we can get different bosonic topological orders. So U equals 2 bosonic quantum Hall, toric code, Ising topological order, etc. So in D greater than 2 spatial dimensions, we get distinct phases even in the absence of zero form global symmetries, again, as Hota discussed. And these distinct phases carry distinct topological orders. One thing I should mention is that for the case of pure states, a non-trivial fact proved by Hastings is that these 2 equivalence relations are equivalent. So classifying gapped Hamiltonians is the same as classifying ground states. So that's a non-trivial statement proven by Hastings. This will break down in the mixed state case, so that's why I want to flag that. Okay. Sorry. So again, I won't go spend too much time on topological orders, and it was introduced earlier this week. So it's the gapped phases of matter which have fractionalized anionic excitations and locally indistinguishable ground states when we put the system on a non-trivial manifold, and they're classified by these so-called unitary modular tensor categories. And again, just to remind you of the modularity condition, it's that every anion braids non-trivially with at least one other anion in the theory, right? So that's the modularity. Okay. And these topological orders, it's been known due to Kitaev that they serve as error-correcting codes, right? So it's very natural to ask, okay, what happens to these states when we add noise to them? So that's what we'll do. Okay. Again, I won't spend too much time on this since we saw this, but the universal data for a UMTC So some category C, we have some finite set of simple objects, which are anyons in the theory. They satisfy some fusion rules. There are physical constraints. There should be a unique vacuum. We saw these F symbols. And then, of course, the theory is braided. So we have the R symbols as well, which satisfy a hexagon equation, right? So we saw this in Julien's lectures. Okay. So I can also give you the gauge invariant data, which are the quantum dimensions of each anion, the topological spins, the total quantum dimension, and then the braiding phase between two anions, which is just defined in terms of the R matrices. So this is a belief. I'm not aware of a proof so far, but we believe that the ground states of local gapped Hamiltonians can only support unitary modular tensor categories, at least in 2+1 dimensions. This is the belief. What is known is that just braided fusion categories, anion theories that are just braided fusion, can happen on the surfaces of 3+1D theories, right? So again, that'll become important later on. Okay. And this is just stated formally, the definition of braiding non-degeneracy. So for every anion in C, it should braid non-trivially with at least one other anion in C. So that's modularity. One notion is that of anion condensation. So anion condensation is a formal map. It's an algebraic map that takes you from one theory C to a different theory C mod A, right? So if I want to condense an anion A, so strictly speaking, what we're doing is we're gauging the symmetry corresponding to this anion A, but we just use the language of anion condensation. So I'll treat these two notions the same way. I don't mean there's a Hamiltonian and I'm tuning a term in the Hamiltonian. I just mean there's an algebraic map, which is what I'll mean by anion condensation. So I want to go from a theory C to one where anion A is identified by the vacuum. That's what we mean by condensing A. So I'm promoting A to a local excitation. So it's very straightforward to show that only bosonic anions are allowed to condense. And when you condense an anion A, you can think of this as kind of a three-step process. So three things happen. Any anion that braids non-trivially with A is confined. So it's gone from your theory. It's not a well-defined excitation. Any anion that only differs up to fusion by A, those become the same because A has become the vacuum. It's in the vacuum superselection sector. So if C and B were different just by A, now C and B become the same in the condensed theory. And then in non-abelian theories, there's one extra step, which is that of splitting, that certain anions are allowed to split. So in the Ising, double Ising anion theory, if you try to condense psi bar for the experts in the audience, it splits. Yeah, for me, it's the algebraic, the procedure here that I'm thinking about, not the tuning of a term in the Hamiltonian. Yeah, so splitting is, so if you have some deconfined anion that's left in your condensed theory and you try to fuse them, and the vacuum can show up twice, right? So you could have, for example, so if I take, double Ising, and then I try to condense psi bar, for example. And then if I looked at, for example, sigma cross sigma bar, so I would get 1 plus psi, sorry, I think I want bar, cross sigma sigma bar, right? I would get 1 plus psi plus psi bar plus psi bar psi. But this is condensed. I think I'm getting this wrong. But the main fact is you get what would be a deconfined anion in the uncondensed theory, but now it's identified with the vacuum. So the vacuum is appearing twice. So then this anion has to split. Oh, so you can think of it as, it's like E plus M. It obeys the same multiplication rules as E plus M. Yeah, it's not simple anymore, thanks. Yeah, that's what I mean. Yeah, exactly, thanks. Yeah, it becomes a non-simple object. Okay. Right. No, it's non-trivial, but yeah, you can do that. Okay, so here's a model that we've seen multiple times, which is the D equals 2 toric code, just to set notations defined on the square lattice, qubits on links, Pauli X and Z operators, sum of two commuting terms. So the star term in my convention will have X's, and then the plaquette term will have Z's. Of course, you know the ground state of this Hamiltonian can just be written as this loop soup, right? So it's this complicated superposition with all allowed closed loop configurations in the X basis. And if we take the system and we put it on the torus, then we get four locally indistinguishable ground states, right? And this is basically the fact that, this is why it serves as the topological quantum memory. These four ground states, I can encode two logical qubits, right? So out of my physical qubits, I make these long logical qubits, and these are stable to local perturbation. So that's why this is a topological memory. Again, we saw the excitations. So the ground state is just given by all the stabilizers or all the terms in the Hamiltonian being +1. If I just apply a string of Pauli X operators, I'll only violate two terms, so I'll create two excitations. Likewise, if I just apply a string of Pauli Z operators, I'll just violate at the endpoints and I'll get two excitations. So these are the E and the M anyons in the toric code. So all the anyons in the theory are just 1, E, M, and F, where F is the composite of E and M. Right? The fusion rules are here, so E fuses to itself to give the vacuum, likewise for M, and then E and M fuse to give F, which is a fermion. Okay, so I'm going fast because we've seen this a few times. And then, of course, the non-trivial statement is that, if I take a loop of Pauli X operators and it goes around sort of a string of Pauli Z operators, as long as they cross once, I pick up a phase -1. Right? So this is just saying I take an M and I braid it around an E, and I pick up a phase of -1, and this is topological, right? It doesn't matter what the shape is, as long as I just cross an odd number of times, I'll pick up the same phase -1. If it's even, then I'll pick up a phase 0. So this is the property of the toric code phase. Okay. So as was discussed in Hotat's talk earlier today, right, we can also think of topological order from a symmetry perspective. So if you take the toric code, then any closed loop of these string operators, right, is a symmetry of the ground state. So the ground state satisfies this E symmetry and this M symmetry, and these are these one-form symmetries. Now on the lattice, these are not topological, but that's, I don't want to get into that right now. Okay. So we can characterize topological order just in terms of these generalized symmetries, right? So in general, there'll be this UMTC data. And this property of the ground state is robust, again, as Hotat discussed. One-form symmetries, when they're emergent, right, you can't get rid of them. They have some stability. So explicitly, if we want to see this in the toric code, let's say we take the exact toric code ground state, and then we just add some Pauli X and Z operators, right? So on each site, we just apply Pauli X and Pauli Z operators. So we know when Hx and Hz are 0, we're sitting at the exact toric code ground state. The ground state degeneracy is 4. But if I take the limit of Hx going to infinity, then I know I'm in the X paramagnet, where the ground state degeneracy is 1. If I take Hz to be infinitely strong, I'm in the Z paramagnet. The ground state degeneracy is also 1. So somewhere, the gap has to close. And it turns out that everywhere, until the gap closes, you're in this toric code phase. And even though you no longer have the exact E and M symmetries that you had at the fixed point, you can still find emergent one-form symmetries. So these are fattened Wilson loop operators, and you can define them everywhere in this phase diagram. And they diverge exactly when you cross a phase transition. So these one-form symmetries are emergent throughout the toric code phase, and they fully characterize the toric code. So we can
require them to be actual symmetries in some low energy sector of
just for the
Hilbert
ground
state
state.
or whole state?
No, I just require them.
Of course, for the ideal model that works for the whole spectrum.
Exactly. But they're emergent if they're symmetries of the ground state only. I only require them to be symmetries of the ground state. Yeah. Oh, so in general, if you take some quantum double and you deform it, you can find kind of fattened Wilson operators. You just dress your string operators, and closed loops of those will still leave the ground state invariant. That would be the exact symmetry. That's the emergent symmetry away from the fixed point. Right. That's right. That's right. No, it doesn't commute with the Hamiltonian. It's just a symmetry of the ground state. Yeah. Only on the ground state. That's the sense in which it's emergent. Okay, so we've seen, vast generalizations, string net models, quantum doubles, but just for simplicity, let me just focus on what we call topological stabilizer codes. So now on my Hilbert space is still defined on, local Hilbert space is still defined on links on the square lattice. And instead of thinking about qubits, I'll just think about qdits, define generalized Pauli operators which satisfy this algebra. And then I can define a Hamiltonian, which is still a sum of commuting terms. And these thetas are going to be my local stabilizers. So I have these stabilizers, they all commute, and they generate my stabilizer group. And then the code space is just identified with the ground space of this Hamiltonian. It's given by the set of all states which are invariant under all the stabilizers. So just a Z degeneralization of the toric code. It turns out that you can realize all abelian topological phases that admit gap boundaries, so anything that's not chiral, using Pauli stabilizer models. Right? So any abelian anion theory with gap boundaries can be realized as a topological stabilizer code. I'll remind you that abelian topological order, it's fully specified by its anion types, fusion rules, and braiding statistics, right? Abelian anion theories are simpler, of course. So you have some finite set of anions, their fusion rules, and then in this case, the braiding statistics are just a U1 phase. Okay. And then modularity, again, is just the fact that for every A and C, there's a B that braids non-trivially with it. Okay. So again, in this case, anions are created by some string-like operators. So you don't violate the stabilizers in the bulk, right? So all the stabilizer plus one in the bulk of the string. Just at the endpoints, you violate a couple of the stabilizers, and those are your anions. And closed loops, again, give you one-form symmetries in this case. And then the logical operators are given by the non-contractible Wilson loops. And they give you a representation of the Pauli algebra on the code space, which tells you that there are logical qubits encoded in the system. Okay, so that was a lightning quick review of topological phases. So now I'll continue to define what I'm going to do to these states, right? So general strategy is going to be take ground states that I understand and just apply a local noise channel to it and see what happens, right? And I want to characterize the decoherent state in terms of its strong and weak symmetries, and I'll define what those are shortly. The reason I'm taking this perspective is there's no Hamiltonian anymore. I don't have a notion of a gap. Right? So the usual ways that we have of thinking about phases of matter, right? That there's some Hamiltonian, it has a ground state, we're deforming that. None of that works anymore. I just have a state and I'm deforming it in some way and I want to ask, is it in the same phase or not? So I can't rely on our usual notions of H and a gap. So I'll just turn to symmetries because as we know, symmetries allow us to think about phases of matter. Okay. So
you say there's no notion of a gap because you have a super operator that propagates a density matrix.
Yes.
There's an eigenstate with eigenvalue 0, which is the steady state, or
Yes.
maybe a finite number of them. But then you can look at perturbations.
So that's a
away,
great point. That's a
and
great
you
point.
can do the spectral theory of the super operator.
So that's a great point, but this is a non-Hermitian operator, and non-Hermitian operators are not stable to deformations, right? They're not epsilon stable. So the gap of the super operator is actually not a good quantity to think about phases of matter. You could make a small perturbation, and you'll end up somewhere far away. No, this is not, it turns out this is not a good notion of a gap. There is a notion of a gap, but it has to do with an information theoretic quantity. It's not the spectrum of the superoperator. You could think about the pseudo spectrum, perhaps, since that's, and maybe Tibor can say more about that since he's thought about steady states. But yeah, that's kind of the obvious thing to do, but it doesn't work. Okay, so to get kind of our general result, we use three approaches. One is just to study exactly solvable models. The other is to think about mixed states as pure states in a double space. And then third, just use the general framework of category theory. So here I'll just focus on the first one. Okay, so what are the noise channels that I'm allowed to apply to my system? I want to consider finite depth quantum channels. So I have one way to think about these is the following. I have some initial density matrix. Let's say it's in some pure state. Then I just add some auxiliary degrees of freedom in a many-body product state. And then I couple these via some local Hamiltonian, and then I trace out these auxiliary degrees of freedom. So what this will do, it'll map my initially pure state to some mixed state, or I'll take some mixed state to sigma rho, where this is just some stochastic mixture of pure states. So in the Krauss operator representation, I can think about it in this way, where I have some finite number of Krauss operators, which have to satisfy this completeness relation because it's a CPTP map. The continuous time version of this is nothing but the Lindblad equation that some of you might be familiar with, where again, all the coherent evolution is encoded in the Hamiltonian, and all the incoherent processes are just given in the jump steps. And I'm going to demand that either my cross operators or my jump operators and Hamiltonian are all spatially local. So this is what I'm allowed to do to my state. Okay. Oh, you just trace them out. I'm not measuring them. I just trace over them. Yeah, there's no measurements in this story. I just trace over them. Or you can think of I measure them and then I forget all the measurement outcomes, which is morally the same thing. Yeah. So you could measure them and then just forget the measurement outcomes. Yeah. Exactly. Yeah. Okay. So in open quantum systems, there are actually two notions of symmetries. So there's a notion of a weak symmetry and a strong symmetry. Okay, so what's a weak symmetry? So suppose I have a system coupled to an environment, and if symmetry charges are allowed to leak from the system to the bath, then obviously the symmetry charge is not conserved in the system. This is what we call a weak symmetry. Okay, so that's the case when the system plus environment together conserve charge, symmetry charge, but the system by itself does not. But sometimes you could have a situation where the system by itself conserves charge, even though it's coupled to the environment. So for example, what could happen is you're exchanging heat with the environment, but you're not exchanging particles, right? So dephasing is an example of this. Dephasing noise, you only exchange heat or energy with the environment, but you don't actually exchange particles. So in this case, you would have a strong U1 symmetry. Okay, so a strong symmetry is when charges cannot leave the system. So you really have a conservation law in the system. And there are many interesting physical consequences of strong symmetries, such as multiple degenerate steady states, etc. Sorry? You could, indeed, yeah. Oh, okay, good. So so the Krauss operators have to be symmetric by themselves, or they have to be symmetric on average. Right, so on average is the weak symmetry. If each of the Krauss operators individually respects the symmetry, that's a strong symmetry. And likewise for Lindbladians. Yeah. So taken together, right? Like let me go back. Yeah, exactly. Okay. So at the level of a density matrix, right? If I have my density matrix, which is a stochastic mixture of some pure states, a weak symmetry just means I have an ensemble of asymmetric states, but the density matrix is symmetric on average. So each of the elements can pick up an arbitrary phase in this case for weak symmetry. But for a strong symmetry, each state in the ensemble has to be symmetric. So it has to pick up the same phase, right? So that's the difference between weak and strong symmetries. So if we just had strong symmetries, we're back to the pure state case. So we kind of understand that. If we just have weak symmetries, we don't really get any interesting physics. I put a star here because I'm mostly thinking about invertible things here, but one can think about non-invertible weak symmetries, and then that's a slightly separate story. So it's really when we have a mixture of strong and weak symmetries that we expect something fundamentally new to arise in the mixed state context, and that's what we want to understand. Okay, so here are two equivalence relations for mixed states. I should say that there's not yet a general consensus on what the correct equivalence relation for mixed states is. So I'm just giving you two that we use. So the first one is the following. Two density matrices, we say they're in the same mixed state phase of matter if there exists a finite depth quasi-local channel such that you can go from one to the other, and there's another channel that takes you from rho 2 to rho 1. It's kind of trivial why you need this two-way channel connectivity, because for any mixed state, I could just tensor in ancillas, do local swaps, and then turn it into a trivial state, right? So it's important that I can go back as well. And of course, channels are not reversible, so this is in general some other channel. So that's one definition that generalizes the finite depth local unitary. Yeah. So the gap of the Lindblad is not a good quantity to think about phases. Yeah, but so if so yeah, okay, so let me give this definition. Maybe this will help answer your question. So I could define another notion of a mixed state space. So I'm not going to use the gap of the Lindbladian, but I'll define, so this is work by Tim Shea and company. So I can look at the conditional mutual information between three regions A, B, and C. So conditional mutual information between A and C conditioned on B. We know that for gap ground states, this decays exponentially. And so if I start from some rho naught, and I do finite time local Lindbladian evolution, and this Markov length never diverges, then I'm in the same phase. And if this Markov length diverges, then I'm in a distinct phase of matter. So this would be a definition in terms of Lindbladian evolution, but it's not using the gap of the Lindbladian. And a non-trivial statement is that these two are not equivalence relations. So in the Hamiltonian case, right, grounds, deformations of Hamiltonians that don't close the gap and classification of ground states under finite depth local unitaries are in one-to-one correspondence. Here, the top definition is strictly stronger than the bottom definition. So you get a coarser classification under definition 1 and a finer classification under definition 2. Okay, so that these are two distinct equivalence relations. And we're still kind of sorting out how to think about the equivalence relations for mixed states. That's a good question. In general, we don't know. You have to think about it numerically. Yes. Yes, you can have strong to weak symmetry breaking. So in one, yeah, so that's a possibility. So if you have some general G symmetry in a mixed state, you could break just G completely, or you could break G in a strong to weak way, and then that could break to nothing. Sorry? So strong to weak, strong to weak. Oh, yeah, so there are, so for U1, for example, U1 strong to weak symmetry breaking, there is a notion of Goldstone modes, but I haven't worked out the counting yet. Yeah, but that should be straightforward to do. Okay, so let's go back to the toric code. Just recall that the symmetries of the toric codes, we have this one form E symmetry and a one form M symmetry, and recall that applying an X operator to the ground state just creates a pair of M anyons. Okay, that's all we need. So I'm going to apply a local quantum channel to the toric code, and it takes the following form. So it's locally generated, and locally with probability 1 minus P, I do nothing to my density matrix, and with probability P, I just apply the cross operator X. Right, so this is my quantum channel, and I'm going to do it on each site. That's for steady states that they have a uniformity condition. That's separate. Yeah, that's not really all. Okay. So what does this quantum channel do to my state? It'll turn my pure state into a stochastic mixture of states, which is arbitrary numbers of pairs of M anyons pinned. Right, that's what this density matrix is doing. Okay. So this is an old problem. This was studied by Kitaev and Dennis back in 2001, where they were looking at the toric code, but we're just going to return to it. So when P is equal to 0, we're on the toric code fixed point, and it's known that there's some decoding transition into the trivial phase, or what was thought to be a trivial phase. And at this fixed point of P equals 1/2, where I'm applying maximal decoherence, this quantum channel just acts as a projector, so I can just study it analytically. So let me just ask, what are the symmetries at this fixed point of P equals 1/2? Okay. So at P equals 0, we just have both of the Z2 cross Z2 one-form symmetries as strong symmetries. And we know we get a topological quantum memory, and the corresponding anion theory is just that of the toric code. At P equals 1/2, we have a strong Z2 symmetry, and one of them gets broken down to a weak Z2 one-form symmetry. Oh, I mean when P is equal to 0, where there's basically no channel being applied, and P equals 1/2, where you apply maximal decoherence. So those are the two endpoints of this. That's all I mean. Yeah, where the channel acts as a projector. Thanks. So at p equals a half, one of the symmetries is just getting broken down to a weak symmetry, but you still have the mixed anomaly between them. And as a consequence, there's no longer a topological quantum memory stored in the system, but there is still a topological classical memory in the system. And if you ask what the anion theory is, or what the strong symmetries of the ground state are, they just correspond to those of 1 and m. So now you have a transparent anion in your theory. Okay. No, so I'm applying X. Yeah, so I'm not condensed. So I'll get to this in a little bit. It's different from proliferation. It's different from condensation, right? Because it's happening through this channel. I'm just turning my state and I'm pinning this kind of stochastic mixture of M's, right? So clearly the M1 form symmetry is still unbroken because it just commutes with this channel. So that's still a strong symmetry. But the other one, the Z1 form symmetry gets broken to a weak symmetry. So if I think about my code space, I no longer have, two anti-commuting one-form symmetries as strong symmetries. And so I don't get a logical qubit anymore. But I still get a topological classical memory because one of my loops is still well-defined on the torus. It's just the toric code. Yeah, it's still modular. Yeah. It's double toric code, yeah. That's right. That's right. Right. So this mixed state with classical topological order is distinct from a trivial mixed state, but only under this local Lindbladian deformation definition. Under this definition of finite depth quantum channels, it's totally trivial. Okay. I can also say something about kind of analogs of excitations, but maybe it's best to discuss that offline. So that's kind of a simple example. Here's a different example. I can just take the toric code, and now I can add fermionic noise. So noise that locally creates these F particles, right? And just look at maximal dephasing. So again, at p equals 0, we just have the toric code. At p equals a half, again, I can ask what are the symmetries. And here it turns out that we have a strong anomalous Z2-1 form symmetry because the anion theory is just 1, F. Just 1 and a fermion, but an emergent fermion. So this is the simplest example of what I would call an intrinsically mixed state topological order, right? So if I have a two-dimensional theory of bosons, right, as the ground state of a local Hamiltonian, we don't know of any way to get this anion theory in the ground state, just 1, F. I should have some boson in my theory. But as a mixed state, I can indeed realize just 1, F as my anion theory. And again, I should specify that by anion theory, I really mean the analog of the ground state here. I'm not talking about analogs of the excited states. That's more subtle. Oh, because under the quantum channel definition, I can just trivialize it. There's a finite depth local channel I can apply that just trivializes it. So yeah. Whereas this one, because it's anomalous, I can't get rid of this anomaly under finite depth quantum channels. Yeah, thanks. Oh, I have a fermion in the theory, right? So if I try to put it on a background without, yeah, exactly. Okay. Yeah, we always use two-way connectivity. Yeah, so I can also create 1, M from the trivial state. Which one? The one? Okay. Those are distinct phases. No. You can't go from 1, M to the full toric code using a finite depth quantum channel. There's no way, right? Indeed. Yes. That's right. So under the definition of this local Lindbladian deformation, those are distinct phases. So the Markov length will diverge if you try to go from 1, M to the trivial phase. Right? So this is why we're specifying the different equivalence relations. So if I pick the second equivalence relation, then 1, N is non-trivial. A simple way to think about it is that the definition under quantum channels only cares about anomalies of strong symmetries, whereas the definition in terms of these local Lindbladians, it also cares about anomalies between strong and weak symmetries. So in the 1, M theory, there's no anomaly for strong symmetries. That's why it's trivial. But there's still a mixed anomaly between the strong M and the weak E. And that's why it's non-trivial under the second definition. That would be fair. But that's, you missed some data, right? Because if you just did that, then either under fermionic noise or M noise, you get the toric code in the double space. So I'm condensing FF bar or I'm condensing EE bar, I still get toric code in the double space. So it's really important to think about symmetries of the density matrix, not the choice. Yeah. Thanks so much. Okay, so this is just a way to generalize to stabilizer codes. So I can just take a density matrix in the code space of some stabilizer code, add some noise. I'll choose noise that locally creates some anyons, so just string operators, and then just look at maximal decoherence. And what's going to happen is that your noise is going to give a factorization of the code space, right? So in a stabilizer code, the Hilbert space is given by the code space and then its complement. And what noise does, this kind of noise, what it does, it factorizes the code space into what's called a gauge subsystem and a logical subsystem. And this is just the definition of a subsystem code. So some of the symmetries remain as strong symmetries, some of them get broken down to weak symmetries, and just thinking about anomalies between them lets us classify mixed state phases. No, I'll generalize in just a second. Yeah, so here so for now I'm just considering, stabilizer codes, but I'll generalize in just a second to categories, yeah. That's right. Yeah, this is a fully quantum mechanical system. Yeah. It's just the fact that some of the symmetries of your original state, once I add the noise, some of them remain as a strong symmetry. So action on the density matrix just from one side leaves it invariant. And then some of the other ones you have to actually conjugate and they become weak symmetries. Exactly. So here I'm in the low noise limit and here I'm in the large noise limit, right? But it's still quantum mechanical in general. Okay. So good. So topological order in the decoherent state is relatively straightforward to understand. It's just given by anyons in C that braid trivially with the set of decoherent anyons. Right? So the topological in the decoherent state, if I decohere some set of anyons, let's say A hat, it's given by the set of all anyons which braid trivially with the set of anyons in A hat. This is in general some unitary braided fusion category. It does not have to be modular. So basically, some of the anyons become transparent. You can't detect them anymore. Okay. So there's a notion of this gauging out procedure for maximal decoherence. So for these stabilizer codes, one way to think about it, I'm just taking string operators for my set of anyons A hat, which I'm decohering, and I can just form a gauge group out of those. Right, so I have a stabilizer group. I just append the string operators and form a gauge group, and then I take its centralizer, and that's my new subsystem code. And then again, you'll get that the resulting anyons are just given by this braided fusion category or braided fusion theory in general. And so this is a way to generate chiral or non-modular anion theories starting from non-chiral UMTCs. I'm always starting from a non-chiral UMTC, adding some noise, and I can peel off part of the state and get something that's pre-modular or even chiral.
I don't know if you can hear me from online, but
and I just add noise that kills off half of it, right? So Z3 factorizes into Z3(1) and Z3-1, and I can just add noise that kills off one of them. Or let's say I take double semyon and I just add S noise, and that'll just give me the anti-chiral part.
I don't know if you can hear me from online. I had a
So just a comment on this gauging out versus anion condensation. So again, anion condensation, only bosons can condense. Some anions become confined, some become identified. And here you're coherently proliferating anions. Rather than this gauging out procedure, arbitrary anyons can be gauged out. It doesn't have to be just bosons. You can even gauge out fermions or semions or anything. Some anyons do become confined, but anyons are not identified. So it's a distinct mechanism. And that's why you're allowed to get these braided fusion categories. And so one nice picture that Apoorv was hinting at is you can always think of a density matrix as a pure state in a double Hilbert space. And there, this gauging out procedure is exactly anion condensation, but in the double Hilbert space. And that's a convenient tool that we can use. But at the end of the day, we should always come back and think about the physical density matrix. Okay, so I'll just flash quickly the general result going beyond abelian theories. So I take some general UMTC, C, and I gauge out a proper subset of anions A hat and C. And then the intrinsically mixed state TO is just given by this constant. Okay, so it's given by the set of all anions in C that braid trivially with what I'm decohering out. And there's a nice theorem by Muger that I only get a UMTC if the set of anions that I'm decohering is itself a UMTC. So in general, you just get some non-modular braided fusion category. So pure state topological order is just given in terms of strong symmetries. Classification is given by UMTCs. And intrinsically mixed state topological order cares about the mixture between strong and weak symmetries, and its classification, at least we conjecture, is given by these non-modular braided fusion categories. And one nice picture for this is that we know that we can realize these non-modular theories on surfaces of 3+1D topological orders. So those of you that are familiar with Walker-Wang theories, if the input to a Walker-Wang is non-modular, then its surface realizes a non-modular anion theory. And essentially what our noise is doing, it's a physical mechanism for just tracing out the bottom, right? And I'm just left with the top. So that's kind of just a very simple picture. But we're doing it through local noise instead of tracing out. Okay. And we've generalized this to 3+1D, where the classification is given by braided fusion 2 categories. Okay. So this interplay between strong and weak symmetries gives us topological phases that are unique to mixed states. Our work also kind of showed that this two-way channel equivalence is a little bit too coarse to fully capture the structure of mixed state TOs because it cares about strong and weak. And one nice thing practically is that it's a nice way now, you can use noise as a resource for state preparation. So we know that chiral states are hard to prepare. So fine, just use your unitary to prepare a non-chiral state and then add local noise to just peel off part of the state and get something that's chiral, right? So noise can now be used as a resource. Yeah, the noise is engineered, so there's no free lunch. Yeah, indeed. So, okay, so I've totally run out of time, so I'll just stop here and take questions.
How should I define the weak one-form symmetry, the analog of this S rho, S dagger equals rho? What is the analog of that for non-invertible one-form?
Let's discuss that offline. Yeah. You can't always realize a any given symmetry as a weak symmetry. Yeah, so Kramer's-Wanier, if you wanted to define as a weak symmetry, right, you can't do it unless there's a Z2 strong symmetry that comes along for the right. Yeah, let's discuss that offline.
So I got a little lost. In which case did you get the classical bit, and in which case did you get the subsystem code?
So you always get a subsystem code. Whether or not the subsystem code encodes quantum memory or not depends on the structure of the strong and weak anomalies. So if you have, in the subsystem code, if you have strong one-form symmetries which have some self or mixed anomalies, you get a quantum memory. If they only mix with the weak symmetries, then you get a classical.
Thank you.
Yeah. Yeah, so you just need to find a finite depth local channel that takes you from row 1 to row 2. And then I need to find another one that takes me from row 2 to row 1. Oh, I can imagine I just take my state and then I just tensor in some ancilla in a trivial product state, right? I can just do local swaps, right? Which is a local process. And now I've turned my state that's totally into, so I can take any density matrix and turn it into a trivial product state, to a local quantum channel, just by doing swaps. So it's important that I can go back.
I still can't see why The requirement of going back solves this problem.
Otherwise, every state would just be trivial, right? If I only required one way, then every state would be equivalent to the trivial state. So what you're really saying is there's some quantum information stored in this state, and the same quantum information should be stored in the other state. And that's the requirement of being able to go back and forth between them.
So I have a question about your claim that you can create like new type of states that are chiral while the original one is not chiral. But any measurement you will do on this decohered state has actually an equivalent measurement on the original state that will give you exactly the same outcome, because you can just conjugate any observable through your channel.
Yes.
And therefore, this new state might be in a different phase, but any observable is actually already present in the original theory. So what does that mean then? To say, what is the meaning of the physical meaning of what you say?
This is a great question. So indeed, so it would only be in terms of some information theoretic quantities, some Renyi 2 quantities, that you would be able to see this chirality. In terms of any physical observable, I agree that it's not chiral. I just mean that the bulk anion theory is chiral. Right? Whether or not that means that you get gapless interesting edge modes or anything like that, we don't know. Yeah, that's a good question. And we don't expect that that's true. But in terms of information theoretic quantities like Renyi 2 observables, you should be able to see this chirality. But I agree that's not physical.
Like in the pure state case, there's an algebra structure, and you can classify all the possible condensable algebras. Is there some analog of that?
We're, oh yeah, yes. Yeah, so we did that, Apurv did that in their paper. So indeed, you can think about it from the double space perspective, right? So the trivial way to do it is think of your pure state as a double state, right? Now you just think of all the condensable algebras there, but you have to put the condition that you're dealing with a density matrix. It has to be positive and Hermitian. So you can get everything you get in a bilayer, except those that violate positivity and hermiticity.
So I'm not talking about the SIM-TFT. I'm just saying in the topological order, you said there's a subset of anyons that you can gauge out.
Yeah.
So I just have that UMTC or non-modular TC. How do I like enumerate all possible gauging out like sets of anyons?
It just has to be a proper subcategory of the category you're starting with. That's it. Yes, you start with C, and any proper subcategory of C can be gauged out.